light as waves. We are going to talk about how light, which is electromagnetic radiation, appears as a wave. And in order to do so, we're going to look at a diagram where we see light represented as a wave, and there's two terms called the crest and the trough, where the distance between two crests or the distance between two troughs is what we call wavelength. Right, so remember that, please. Wavelength is the distance between two crests or troughs, and I'm going to refer to wavelength now. Let's look at the slide in front of us. In talking about light as a wave, we're going to refer to this equation here. C is equal to lambda by nu, where c is equal to the speed of light, lambda is equal to wavelength, and nu is equal to frequency. Let's break it down, and I'll start with c, which is a constant, and this is called the speed of light, and it has a constant value of 3 by 10 to the 8 meters per second. Because speed of light is a constant, that means for light, which acts as a wave, we should be able to, given its frequency, determine its wavelength, or vice versa. Or if we have the wavelength and frequency of electromagnetic radiation, if we multiply those two values, we must get C, which is a constant. Let's look at lambda and nu. I'll start with lambda, which is called the wavelength. As stated before, the wavelength is the distance between two crests or troughs, and wavelength is given a unit called nm or nanometer. Frequency represents the number of waves, or I guess the term may be oscillations, waves per second that electromagnetic radiation will make in a specific distance. So frequency refers to, very simply, the number of waves, right, or the number of vibrations the wave makes, such that frequency is measured in a unit which is per second. So we look at the number of waves per second, and the unit for frequency is either 1 s to the minus 1, which is per second, or what we call a hertz, where 1 hertz, as you can see, is equal to 1 s to the minus 1. If we take this equation and we rearrange such that frequency is equal to speed of light over wavelength, what we see here is a relationship between frequency and wavelength, such that frequency is indirectly proportional to wavelength. What this means is a high frequency should be equal to a short wavelength, and a low frequency should be equal to a long wavelength. That is, as one entity increases, the other decreases. We'll talk about this a little more later on. Let's look at an example where the equation C is equal to lambda by nu is used. And one example here is, let's say you're given that red light, which is a form of visible light, has a wavelength of 615 nanometers. You're given the conversion for a nanometer, where it's equal to 1 by 10 to the minus 9 meters. And given this wavelength, can you then calculate the frequency of this red light? You can use the equation, and I see they have the letter F where it's supposed to be nu. but we rearrange our equation to calculate frequency such that if we put the speed of light c over the wavelength and we make sure our units are correct, so meters per second over meters, where the two units cancel off, will give us frequency in per second or hertz. So you had to do a conversion here where light was given in a wavelength in a unit of nanometers, and you converted nanometers to meters in order to solve for frequency.